Hi. Okay, this is the new setup, back to the PowerShot camera. I hope everything's working. You can see everything and hear everything, and it's nice and clear, and you can read the board. So today we're going to try to finish off with NP completeness. So this is going to involve me explaining sort of Cook's theorem using assembly language, and then explaining Cook's theorem using Turing machines, which means I have to tell you what a Turing machine is. And then I'm really going to sort of explain Cook's theorem and look into the implications of it and say why it's so important and how it's stated and the implications. Okay, so in the previous classes we saw that you can turn certain problems into other problems in polynomial time in such a way that, so given an instance, for example, of clique, you can turn it into an instance. It's very easy, actually, to turn it into an instance of independent set, such that the instance of clique is a yes. That is, you're given a graph G and a clique and an integer k, and you're asked, is there a clique of size k in G? And you can turn it into an instance G prime and k prime of independent set, such that G prime contains an independent set of k prime, of size k prime, if and only if G contains a clique of size k. So to do that, you just complement the graph. You remove all of the edges that are there, and you add all of the edges that aren't. So that was obviously that takes only polynomial time. So you have this equivalence between problems up to, well, in this case it's pretty tight, but generally up to polynomial factors. So if you find a polynomial time solution for one, you find, for one problem, you find a polynomial time solution for the problems that can reduce to it in polynomial time. So if you can get this to go sort of both ways, it means that the two problems are equivalent. Sort of like we saw before that max sum subarray and max sum subarray in a circular array are equivalent. So they both take, well, the first time we saw that you could do one in n log n, and so you could do the other in n log n, and then we did max sum subarray in linear time, which implies that you can do max sum subarray in a circular array also in linear time. So what we saw was, we started with clique, and we got this nice reduction to, no, it's not going to write, reduction to independent set. Alright, so you can turn these two problems into each other. And then we saw if you can reduce independent set to vertex cover, and vice versa. And then we saw, I forget the exact order, but we saw, I think we saw clique to sat, I think. So remember, that was this idea that given a graph G and an integer k, you could write a formula, a propositional formula of size polynomial in the size of the graph that said this graph contains a clique of size k. Right? So when I said the formula says this, the formula is satisfiable if and only if the graph really does contain a clique of size k. If it doesn't, the formula is unsatisfiable. And then we saw that you could reduce sat to 3 sat, which is propositional formulas in 3 conjunctive normal form, which means it's a conjunction of clauses. Each clause is a disjunction of 3 literals. Okay. And then, of course, sat is a special case, 3 sat is a special case of sat. And then we saw you could reduce 3 sat to clique. So from any of these vertices, you can reach any of the other ones. In each of these, in a constant number of steps, each of these steps takes polynomial time. Composition of polynomials is polynomial. Therefore, if you solve any of these in polynomial time, you solve all of them in polynomial time. So then, I believe we saw you could do ham path. we saw how, given a graph G, we could write a polynomial-sized formula that said this graph has a Hamiltonian path. And then we saw, again, I'm forgetting the exact order, we saw that you could reduce 3-sat to ham path. Actually, we saw you can reduce 3-sat to directed ham path, and I forgot that the reduction from directed ham path to ham path is really easy. You just sort of replace each vertex by 3 vertices, and you can find it online. It's very easy, and I'm kind of embarrassed that I messed that up. But I had been fighting with Zoom and Teams and everything, trying to do the online classes. So sorry about that. If I'd been thinking, I would have put it on assignment 4, but I forgot. So actually what this should say is sat to directed ham path. 3-sat to directed ham path. And you can reduce directed ham path to ham path. Okay? And then we saw 3 colorability. So we saw how to reduce 3 colorability, ooh, this is ugly, to, why did I draw that there? Help, where's my eraser? Why don't I draw this slightly out of the way? So we saw how to reduce 3 colorability to sat. Oh, but this is still going to be kind of a pain, because now I have to show, and then we showed how to reduce 3-sat. Okay, well actually I want a vertex here. We reduce 3-sat to 3 colorability. Now I remember from the previous lectures that we could reduce 3 colorability to 4 colorability, and we could reduce 4 colorability to 5 colorability, and so on and so on. And it's also not difficult to reduce 4 colorability to sat, to write a formula, to just change basically the formula we came up with for 3-sat to say this graph is 3 colorable. Okay? And you can also, of course, write polynomial-sized formulas for Eulerian path. Okay? But we know how to solve Eulerian path in polynomial time, so we don't think, there would be a path from Eulerian path or Eulerian cycle to sat, but there would be an edge from Eulerian path to sat, but there wouldn't be a path backwards, because we don't know how to reduce sat to Eulerian path in polynomial time, because if we did, then given an instance of any of these problems, we turn it into an instance of sat, we turn it into an instance of Eulerian path in polynomial time, and then we'd solve that in polynomial time, and we'd have a solution for the original question. Okay? So remember, sat is this formula satisfiable? In fact, all of these languages, when we're talking about decision problems, yes or no things. Is this satisfiable? Is this not satisfiable? We're not actually asking for a satisfying assignment, but on the assignment, we're not asking for an actual solution. We just want a yes or no. Is there a solution? On the assignment, you're going to see that actually, if you can get a yes or a no, then you can use this yes or no to actually build a solution. Okay. And also you can reduce 2 colorability to sat, and you can reduce 2 colorability to 3 colorability, but again, why would you want to do that? Because we can solve 2 colorability in polynomial time, and we don't know how to solve sat with 3 colorability in polynomial time, and we don't think there is a way. So, okay, that was a review, lightning fast. Well, not exactly lightning fast, but sort of. So the idea is, this, now we can say, if sat is complete, so what does sat mean? What does complete mean? It means that if we could solve sat, we could solve any of these, and actually, so it's complete for the class of problems such that given an instance of a problem, so if you have some problem X, right, what does it take to draw an arrow from X to SAT? So what it takes is to be able to say, given an instance of X, so given an instance of X, we can write a polynomial size formula that says, so let's say given an instance, let's give this a name. Let's call this little x. I'm not sure that's a good name, but okay. Little x, let's call this p. Okay. Given an instance, little x of p, such that x is a yes instance, if and only if a formula f is satisfied. Okay, so that means that given an instance x of p, we write this formula f. So then, if we could solve SAT in polynomial time, we could obviously solve p. Okay, so p would reduce to SAT in polynomial time. Okay. Now, we would also like to say that SAT is in the class of algorithms for which we can write formulas saying that an instance is a yes instance. So SAT is complete for this class. Okay, it's in the class, and everything in the class reduces to SAT. Okay? But that's sort of weird. That was clumsy. You saw, I think I slipped a couple of times in describing that. That's not a natural thing to say. I mean, you couldn't go on TV and say that. I mean, you could, but it wouldn't get high ratings. It wouldn't be catchy. Okay? People would edit it before they put it in a commercial or something. So, but I hope people can see this. So for any problem like this, if you can solve SAT in polynomial time, you can solve this in polynomial time. Okay, and if you can solve SAT in polynomial time, obviously you can solve SAT in polynomial time. And if you can solve any of these in polynomial time, you can solve SAT in polynomial time. Okay? So now we want to come up with something a bit more natural. Okay? So the idea is, remember I was saying we're using SAT like a programming language. I'm not sure that I'm going to finish the first part in the first 25 minutes. I'll try. The review was in the first 25 minutes. So what we'd like is to say, well, if we can obviously, since we can write a formula as a graph, such that the graph has a clique of size k, if and only if the formula is satisfied, right? Because we can reduce SAT to clique, because actually we go to 3 SAT and then we reduce SAT to clique. Okay? So is that more natural? Is it more natural to say SAT is complete for the, or actually any of these is complete for the class of problems such that given an instance of the problem, we can write a graph and an integer k such the graph has an integer k if and only if the instance is a yes instance. That's not, well, none of these problems is that really a natural thing to say. So what we're going to look at is there's another problem that we're going to have here that is sort of a natural thing to say, which is, does a program say, is there an input to the program that makes it say yes in polynomial time? Okay. So that's, I mean, pretty obviously SAT reduces, well, any of these actually reduce to that, because for any of these problems, I can write given a graph, I can write a program that takes an input, and that input would be a clique, for example. So I'm trying to solve clique. Okay, so somebody gives me so this problem is going to be called something like accepts, or accepts. And I'm going to, so let's see that clique reduces to accepts. So accepts is this problem. Let's say given a C program, is there an input that makes it return true in polynomial time? And by polynomial time, I actually mean polynomial in the size of the program. So actually, when I reduce clique to accepts, I will be able to work out exactly how much time I need to give, because I can figure out how many operations the program is going to need to check the input. So what would you do? Well, given to show that clique reduces to accepts, given a graph G and an integer k, you would say, okay, so this is a question, is there an input? So you would write a program, you would hard code the graph G and the integer k into the program, right? And so now it's going to read an input, and if that input is a clique of size k, it's going to say yes. And if it's not, it's going to say no. Okay, could you write such a program? I hope so, because all you have to do is this clique is going to be it had better be a sequence of k vertices, each of them distinct, and then you just check to see in the graph, is there an edge between each pair of these vertices? Clearly this takes polynomial time. So you could actually work out exactly how many steps this program is going to do. So if you can solve accepts, then you can solve clique. Okay. And in fact, if you can solve accepts, you can solve any problem for which you can check a solution in polynomial time. Okay. So accepts is what we call NP complete. NP means non-deterministic polynomial, which means basically you're allowed to guess a solution. Somebody is going to give you a solution. Actually, I think you may have seen non-determinism in 2110. So you're allowed to assume that you're going to be given a solution. If you can check it in polynomial time, then and it's good, then you say yes, and if not, you say no. So if there is an input, then if you can solve accepts, you can solve any problem for which you can check a solution in polynomial time. Okay, which is very powerful. Okay, in the fall semester. When I first taught this course, I started off, I've been really pushing C. People should program in C, and I was giving all my examples in C. And so I started by, I did this, so I began the NP completeness lecture by saying, okay, so I'm going to teach about NP completeness today, but first I'm going to tell you why I love C so much. It's because the GCC compiler has this functionality, accepts. That given a program, it will tell you, it will run in polynomial time, and it will tell you if there's an input to that program that makes it return true in polynomial time. And then I went on and on about how accepts is such a cool thing, and this makes GCC much better because I don't know of any other compiler that has this functionality, and I showed them how you can use this to do incredible things. And then I told them, yeah, so one of the students actually sent me, because I was having them send me SMSs because people didn't want to use Top Hat. People didn't want to pay for Top Hat. So I got an SMS and somebody said, you know, while I was speaking, he said, I've been Googling, I don't know who it was. They said, I've been Googling this and I can't find any trace of this functionality of GCC. Could you show it to us after class? And so eventually I said, yeah, well, I mean, obviously this doesn't exist. And this would be incredibly powerful. This would break all kinds of cryptography, right? Because if somebody, given a cryptographic protocol, you can check a key in polynomial time. I mean, you can compute, you can decrypt in polynomial time. So you'd be able to write polynomial time, if you could write accepts, you could break crypto systems in polynomial time, which we don't think you can do, which we hope you can't do. You would be able to solve all of these problems in polynomial time. Any problem where you could check a solution in polynomial time, you could find a solution in polynomial time. And I said, yeah, that would be really weird. And then this person sent me another SMS saying, I've been played. I have it. Actually, I think I still have it on my phone, but I can't show it to you right now because it's still got the phone number on it, so that would be a breach of privacy. I'm surprised the timer hasn't stopped yet. God. Do I have to restart the camera? Oh, I have 2 minutes. So, okay, this isn't going to be nicely divided the way I want. So we understand what accepts is. And we understand how these reductions work, that we could, why SAT is so powerful. So now, the trick is, instead of saying we can reduce something to SAT, we're going to say, well, it's easy to show we can reduce something to accepts. So I apologize in advance to the people who are ascribing the reductions from ham-path to SAT and three colorability to SAT and stuff like that, because nobody actually does those reductions to SAT. What they do is just do the reductions to accepts, which means they show that you can, given a solution, you can recognize, you can check it in polynomial time, and once we've shown that accepts reduces to SAT, that means since SAT reduces to 3 SAT, and 3 SAT reduces to clique, that means these things are all also in this network. So if you can reduce clique to accept, once we've shown this reduction from accept to SAT in polynomial time, then it means you automatically get that clique reduces to 3 SAT in polynomial time. Okay? So nobody actually does reductions to SAT. They do reductions, they just show that you can check a solution in polynomial time. I'm sorry, scribes, but I was trying to give you some intuition before I just showed you Cook's theorem. why. I mean, this network these reductions are fairly natural. The next, okay. So I actually have like 2 more minutes on this. So these reductions are not so tricky. Cook's theorem, you can see how I could figure, I mean, I did the reduction from 3-colorability to SAT just sort of off the top of my head. Nobody does it, so it's not on the internet. Well, everything's on the internet somewhere, but it's not easy to find. The reduction from 3-SAT to directed hand path is not that bad. The thing I'm about to show you is a little bit hairy, and I mean, if you see it just right off the bat, you wonder where it came from. I mean, it sprang from the mind of Cook, but you wonder where he got it. So if you just tell people Cook's theorem, they think that Cook was just a genius, and this stuff like comes out of thin air, which is partly true, but no, there was a reason. Okay, I mean, there was a chain of reasoning that led him there. Okay, so now I'm going to stop.